Last time we talked about mass transport, and so we were interested in not just this diffusive portion of transport, but also an advective component. And we spent some time talking about that. And so to summarize, we end up with a very similar system of equations we had before. This represents reaction, which we haven't dealt with, and we won't deal with today, but we will ultimately deal with. Otherwise, this looks like identical to our system of equations that we had before, which were something like this for conductance. Because the equation that we're representing includes a term that relates to a second order derivative and also a first order derivative. We have an additional term which is for this advective component. And if we look at this, then the only extra component we need to accommodate is this advective term, which is what? V transpose VA, or the other way around, I'm trying to remember. V transpose VA. So this is, again, looks similar to before. This is shape functions. These are element velocities. These are derivatives of the shape functions. And again, the integral is over the volume of the element. And so we've added this extra term to the system. We solved the problem for both steady state behavior, where we don't worry about this capacitance term. So in other words, where rates of change of concentration are 0. And we found out that we actually have to apply a specific boundary condition at the outlet that stops us from just accumulating mass at the outlet. So that was one consequence of the analysis that we looked at. So you can look at flow of the carrier fluid, typically water, with a concentration or a mass loading attached to it. If you prescribe that the velocity exits the element, then what it will do is it will basically strain the carrier component on the inside, and it won't leave. And so it won't allow it to actually go across that boundary. So we have to put a convective boundary condition to that. And so we'll talk a little bit about that today. We also did a transient problem where this capacitance term is not 0. And we know that the capacitance matrix that we have is no different from the one that we had for steady, Darcy flow. It's components, not the derivatives, but the shape functions, product of the shape functions, integrated over the volume, and has the same physical meaning as before. B transpose B represents the volume of the element, nothing more than that, just distributed between the different locations. And we can make the call as to whether we will do consistent mass or lump mass computations with that. The ones we did in class were lump mass. We developed a one-dimensional element, and we saw how that worked, and we noticed a few issues about stability. And so what we'll do today is we'll take, as in the past, migrate this to be able to look at more than one spatial dimension, more than one-dimensional element, look at 2D. And we'll talk then about the issues that arrive from looking at this first-order term, which all Eulerian methods don't do very well with. And Eulerian is just a fancy way, of course, of saying that you have a static mesh that stays fixed in space, and water flows through that, and it carries components with it. And so, as opposed to a mesh that, for instance, moves with the fluids and would actually follow the advective component, because you're actually making the mesh travel at the advective velocity. And so this behavior of something flowing into it from one side and going out from the other side, according to this first-order term, is tough for Eulerian methods to be able to accommodate. And so we will talk about mixed Lagrangian Eulerian methods to be able to deal with this term, but not today. So I'll do a couple of things today. We'll talk about 2D elements quickly, using heuristic arguments of how to get them. And we'll talk about stability and ways to get around that through using different shape functions to deal with it. Different shape functions which ultimately have their own problems in terms of creating their own unreal numerical dispersion in the problem, which obscures whether you're getting the right answer or not. And so those are the two things we'll talk about today. And we'll perhaps try and do some calculations using COMSOL to maybe provide our first linking between flow systems and transport systems. Because you realize, of course, here that since the behavior of transport is controlled by this advective velocity, you need to get that advective velocity from somewhere, and of course it's the flow regime for the water, that's the carrier fluid, that you have to accommodate. Okay? So first things first, let's try and use this very simple argument to figure out exactly what the advective transport matrix should be for our simplest of two-dimensional elements. So we'll go back to our friend, the triangular element, with nodal values I, J, and M at the corners. We miss K because it's just confusing. We know that this advective matrix is the product of shape functions, velocity within the element, and the derivatives of these shape functions. But we know that when we've developed this element before, we never actually accommodated shape function. You remember that what we did was we said, let's put a surface on top of this element. Imagine the concentrations or the heads being the elevations of sticks above each of the nodes. The plane that goes through the points of those is the equation of a plane, right? A plane uniquely goes through 3 points. And so if we know what the equation of that plane is, we can use that as our mapping function to be able to map the heads from node to node. So we never explicitly define shape functions. And so we will approach this in a slightly different way. So the first thing is as we look at these matrices, we know that this A matrix is the derivative of the shape functions that, for instance, allows us to map concentrations at nodes onto derivatives, gradients of those concentrations in X and Y. Before, when we dealt with it, it was heads at the nodes were linked onto nodal gradients by this in the same way. And so all we're doing is we're exchanging the value of the dependent variable for from heads to concentrations. So we know exactly what that matrix is because we've derived it. And it's a function only of geometry. These terms, A, 2, 1, etc., are just coordinates of the nodes subtracted from each other. And this is 2 times the area of the triangle, which is 1 over the determinant, 1 over 2 times the determinant, which gives us the behavior of this matrix. We are going to assume that within the element that we have velocities which are constant in each element. They aren't necessarily constant in the same in adjacent elements, but they are constant within an element. And if we have those, then the product of these two we can straightforwardly get just by multiplying these two matrices together. We know this, and these are just 2 constant values. We know that these values are nodal coordinates, so both of these matrices are matrices of constants. They don't vary with space within the element. And so the product of those two is also of a matrix or a vector of constants as well. And so with that, the only term that we have to figure out is what this multiplier is. And there is a kind of problem, but really it's not much of a problem. The problem is that we've never defined what the shape functions were for the triangular element before. But what we did do was we talked about what the individual components of these shape functions would be, and we can note that the components of this matrix are all constants, so they don't vary with location in the element. And so presumably we could take this integral of the shape functions multiplied by constants. Well, we can take these outside, right? Can't do it with the matrix equations by writing them backwards, but we can take them outside the integral because they don't change. And so if that's the case, then we just need to figure out exactly what the magnitude of this particular integral is to be able to do that. And to do that, we can just think in terms of physical components as to what the shape functions are going to be. So what are the shape functions going to be? Well, we know that if we take the element and we look at node number I, then the shape function for that is going to be equal to unity at that node, and it's going to be equal to 0 at all the other nodes. And if we map linearly within the element, which isn't an unreasonable assumption, then the shape function is going to look like this. We don't care what the expression is, but it's going to look like this. It's going to be a triangle. It's going to be a tetrahedron, I guess, but not a regular tetrahedron. And it's going to have a peak here, and it's going to be the integral of this individual shape function which forms this is just going to be the volume of this particular shape. And the volume of this particular shape is the area of the triangle multiplied by a third of its height. And so the integrals of the individual shape functions, you can imagine, are just going to be given heuristically by the magnitudes for each of these components multiplied through by the area of the base of this triangle, which is just delta. And so we know what these individual components are. And so now if we want to multiply by this component here, we just have to multiply this this matrix by it. And so it becomes relatively straightforward to be able to just multiply this matrix by the values of a third, a third, a third, and we end up with a 3 by 3 matrix which accommodates all of these components. So no more than that. And so we don't have to figure out what the shape functions are. Just by thinking in terms of what we know about the properties of these individual component matrices. And the key properties, I suppose, are that the product for velocity times the derivatives of the shape functions is, or the A matrix, which is the derivatives of the shape functions, are individually constant. This is constant within the element. This is just the x and y coordinates of the nodes subtracted from each other. And the magnitude of this shape function matrix, in terms of what it physically means when we integrate it, it just becomes the volume of this prism, which represents a third. Well, it's just, you know. So if you take your triangle and you have a height of that triangle being this, if you added those shape functions together, it would just give you this planar surface on the top of here of height 1 high and area of the triangle in area. And so it's just a matter of splitting that up to be able to link it between each of these individual components. Nothing more than that. And so we can develop the triangular element by doing that. If we, I won't bore you with running EG-FEM, but clearly you could see that since we localize these behaviors, that and we know that we do all this the calculation for the conductance matrices in this local element location where we calculate what the element conductance components are, then adding the advective portion is really pretty straightforward. This is, I guess, this is element 1, 2, and you can see this, you know, we come in, this is this K matrix that we want to get, which of course is this term here that includes both of these, right? This overall K matrix is here. This is what we've called our capacitance matrix, and we don't have the equivalent of a mass matrix in that. And so if we look at this, what are the components? You'll see that this is the coefficients of the area, the conductivity divided by the length, so that's A d over L, and the magnitudes are 1, minus 1, minus 1, 1. So this is just our typical, this is our diffusive matrix, which is AD over L, 1, minus 1, minus 1, 1. Not for this geometry, of course. This is for this 2 degree of freedom one-dimensional element. And you remember what were the expressions? Well, I don't remember myself, so let's go back. The expressions for the advective component were just, let's go back all the way. Area times the velocity divided by 2. And so if you look, yes, let me just write that down so we have it in the same place. So This is area velocity divided by 2, and correct me if I'm wrong, but I think it's this, right? It's not symmetric anymore. And if we look at the magnitudes of this, so this is just made up. So this is this first component, the diffusive part, which is symmetric. And the second part is to add to this matrix that we've already defined right here. It's to add another matrix, which is the cross-sectional area of the element, the velocity of flow, which we've defined within the element, presumably as one of our local material properties, which is this magnitude here. So we supply it in this particular case, and we calculate this magnitude, which is 1 minus 1, 1, minus 1, 1. So it's exactly this relationship here. And so that's exactly what it would look like for that case. I think also, so this is what, element 1, 2. I'm guessing that element 2, 2 is probably the same for a triangular element, and is. So in other words, again, it gets localized in exactly the same way. And let's see, this is going to be, so now the diffusion matrix is just the diffusion coefficient in the x and y direction. So it's a unit matrix multiplied by whatever that diffusion coefficient is. We calculate these values to get the magnitudes of the A matrix. So this is the derivatives of the shape function matrix, 1 over 2 times the area of the triangular element, and then the individual components which make that. So this is going to be a it's going to be a 3 columns and 2 rows matrix, right, in terms of size. And then what's going on here? I'm trying to think what I'm doing. So we're zeroing out a matrix. So yeah, so this is, what am I doing here? That's a good question. So this is the A matrix. So this is the sign for A transposed. This is dA. So this is calculating the magnitude of the second order matrix. So this is the diffusion matrix, which is just the regular conductance matrix that we have for the second order term. And then the first order term is going to be the transpose of the velocities multiplied by the A matrix, multiplied by the area of the element times the thickness, and the factor is just going to be this value of a third, which is the multiplier of this. So it's exactly this matrix here. So it's this matrix here. So the area of the element and values of thirds on there. I pull it out, which I think is this here. So it's just 3 by 1. It has values of 1s in it. So it has values of 1 in each of these locations. So it's equal to a third. We zero the matrix is going to store it. And then we take the product of the derivative of the shape functions and the velocity vector, and we multiply it by this B transposed integral component, which is just this factor here. And you end up with it. And so it all gets done in this one location. And so it's really no different from any of the other solution that we've done for just solving the second order diffusion equation. We just have an extra term that gets added directly to this. And we know that if the value for this velocity ends up to be too high, so velocity ends up going in here, if this value of velocity gets too high, then the solution doesn't work out because this first order term becomes dominant and ill-behaved, and the solution falls apart. So it's relatively straightforward to do. So we can do that certainly for to look at the transport case for 2 dimensions. And so we won't do it for 3 dimensions, but it follows directly. And of course you could use shape functions and isoparametric elements to develop it for higher order elements as well. So we won't go through that, but because that's not our particular interest in this class, but you could do that probably for yourselves. So the second part of what, so now we know how to get these elements generically. can do it in one dimension, we can do it in 2 dimensions. By extension of all we know about how to put together isoparametric elements, we could also do it by extension in 2 dimensions for prismatic elements with 4 nodes, or 9 nodes for that matter, and also by extension to 3D as well. So we'll leave it there and not take that any further. But we had this problem before. We found that if we use velocities which were too high, and if we go back to remind ourselves of exactly that, in this very simple example, and I'll back this off, and that is that if we used a velocity that was actually too high, then in looking at flow downstream in this element, if it's diffusion only and you fix the concentration conditions upstream and downstream, then the solution for diffusion only is just linear, just be like Darcy's law, because it's fixed law, fixed first law. If you have advection on top of that, if you have it flowing downstream from your left to your right, then your concentration gets advected from the upstream boundary condition, and therefore it's dominated by this magnitude here. If it's flowing in this direction, then you get the opposite effect in that you, if you like, you advect the, I guess this is now the upstream boundary conditions because it's flowing in this direction, and you get a reduced concentration as a result. The problem, of course, comes when the magnitudes of this velocity become too large, that this becomes larger than your boundary condition, which is obviously an unreal condition. And so we said that before, that that's limited by the magnitude of this, which of course is some description of an in-element Peclet number. And so we know that when we run these kinds of elements, that if we use Peclet numbers, which is just the ratio of the advective to the diffusive flux in the system, local velocity of flow, length of the element, not of the domain, and diffusion or dispersion coefficient, when it's more than 1 to 10, 2 to 10 here, then these Eulerian methods don't work very well, and we have to have some other solution. And so there are a couple of solutions that we can invoke. One would be to make the Peclet number smaller by using lots of elements. And maybe we'll do an example today to be able to see if we can show that working. So that's certainly one solution. So you just change your mesh to be able to get below this threshold, and then you can use the solutions that we've talked about, these Galerkin elements. The other one is to be able to do something with the shape functions, and the solution typically to do, and there are other solutions as well, but the ones we'll look at is in terms of using what's referred to as upwind weighting. And all it does is it changes the amount of influence that you apply in the upstream direction relative to the downstream direction by just using different weighting of the shape functions to do that. And so that's an attempt to be able to get rid of these problems which we've kind of alluded to in what we've done. And if you draw them in kind of cartoon form, the problems are of overshoot. So if this is a picture of a piece of core with the profile of concentration as you go downstream, this is overshoot, this is undershoot. A concentration less than 0 doesn't make sense. A concentration larger than the input concentration doesn't make sense. And also the fact that you get oscillations around the front and also behind the front is a result of this unstable advective term operating. So one way to solve for this, these clearly incorrect solutions, is to use upwind weighting, but the downside with that is that if you provide upwind weighting on this, what you might get is a solution that looks like this solid line here, which would be the true solution from using upwind weighting, but it would not necessarily be the true solution, which might be much sharper, much steeper. And the reason is that when you add these extra weighting functions, you put in extra amount of dispersion in the system, artificial dispersion or numerical dispersion, and you're never quite sure how much of that dispersion you have, right? You never know because you can't define it. And so we'll look at upwind weighting to be able to do that. The other thing that I skipped over, but I'll come back to, is that there are two important features in terms of stability. Stability in terms of the spatial discretization, if you like, and that is that the length scale of the elements have to be small enough to be able to give a good representation of the concentration field. And so that's what really the Peclet number is saying. The other number is Courant number. And the Courant number is a ratio of the, I suppose you can think of it in terms of whether the element actually sees the pulse going through it. So in other words, the numerator, the velocity times delta t is what? A velocity times time is a length. So this is the length traveled. Traveled in delta t. And so if you have a front that's moving at some velocity v, and over delta t it travels this length. If that length happens to be longer than the length of the element, which is in the denominator, then the element physically hasn't seen that pulse. It's gone from upstream to all the way downstream in the time of one time step of your solution. So the physical interpretation of the Courant number is a time step that's small enough to be able to make sure that the front is captured inside the window of your element as it passes through. Nothing more than that. And so for that reason, a Courant number of 1, if the Courant number is larger than 1, it means it will have passed from upstream to downstream without residing in the element, the front. And if it's less than 1, it means it will have been captured within that window. It's the physical explanation of it. And so to be able to make sure that you capture that transport, then you need to choose a time step for your solution which satisfies this criterion, where again this length is the length of some characteristic length scale of your element. So it's the length of a one-dimensional element, or it's the average length of the real. Yeah, tau. For both, yes, both will not work well. Have a problem. Yeah. So that I think by that time step, I think, yeah. So the other thing which haven't really thought through beforehand. So certainly, if you reduce your Peclet number by having smaller elements, then implicitly, I suppose, you increase your Courant number. So you work against yourself. So you have to even further reduce the time step to be able to capture it. So if you have problems, if you're right on the edge of stability, both in terms of the spatial stability and Courant number, in terms of having Peclet numbers and Courant numbers that are around 1, then if you make a finer grid to make a Peclet number, say you make it 10 times finer, so you have a Peclet number of 0.1, which is fine, then all of a sudden the Courant number will go to being 10, and you'd have to reduce the time step by a factor of 10 or by a factor of 100 to get it down to a fraction of to 0.1. And so they work against each other in that regard. So it means that if you have to increase your discretization to be able to accommodate your system, then you need to have a very fine mesh, and you need to do very fine time steps to be able to satisfy both of those criteria for transient problems. And so upwind weighting is one way to certainly get around the Peclet number issue. Not sure what it does on the time step issue. And the concept is quite straightforward. We always think of elements in terms of these shape functions. So if you have a given element, then this is our one-dimensional element, which is just this block. If you draw it in perspective, it looks like this with some area, etc. We think of the shape functions in terms of the requirements: unity at the node in question and 0 at all other nodes. So if we have 2 nodes in this particular case, we have 2 shape functions. And we can look at these shape functions in terms of what we've done before. And so we define them in terms of 1 minus x over L and x over L. So this is just our linear shape functions that we've defined for the previous, sometimes called chapeau shape functions, for those of you who might speak French, because if you look at the next element that's added on here, then this looks like Napoleon wearing a hat. So sometimes referred to as chapeau shape functions. I think it's so French for hat, and so like Napoleon's hat. And so if you think of them instead of being on the element but relative to a given node, where you have one shape function on one side and one shape function on the other side, then these elements, shape functions, look like a hat. What you could do is, instead of using these linear shape functions, you could take them, as we had here, and you could add an extra term to them. And that extra term would change these functions in some way. And if that term is something like this, so this psi is just the location along the element, so I guess uppercase L, right? If you look at the magnitudes of these shape functions, one key component, of course, is that at nodes 1 and 2, the values of x over L will either be 0 or L, and so independently the values will always be, of this second function, are always null at either nodes 1 or 2. So it always gives you this ability to either be 1 or 0 at each of these locations. So this height is still 1, this height is still 1, this intersect here is still 0, and this intersect here is still 0 as well. But in between, it gives a different weighting. And you'll see that these two shape functions are just the, not reciprocal, I guess the negative of each other. And so what you add on to, for instance, this element here, you physically subtract from this element here. So this area above this curve here is kind of mirrored by this component here, as you see here, just because of this, right? Because this term here. And so the easier way to think of these weighted shape functions, I think, is to look at this central node and think what the shape functions look like around this. And so if you look at this shape function that comes to the right-hand side of this node, you have this one. And if you look at the shape function that would be over here, which of course would just be the mirror image of this, you have this component. And so physically what it's saying, I think, is it's giving more weight to the information that comes from upstream than the information that's downstream of this point, right? Just because if you look at these relative weighted areas, this is a big area, so a big weight, this is a positive weight, and this is a negative weight. And so when you add these two together, this, this apparent area is even less because you have to subtract this area from this average area. So that's really all upwind weighting is. It gives more weight to the information that's coming from upstream or upwind, and these are always aligned relative to the direction of the velocities you have in the system. So, okay. And so to be able to implement that, we do nothing more than what we've done before, is we now incorporate these shape functions for the one-dimensional element as a portion which includes 1 minus this eta term. This is this additional term which is either added or subtracted onto the shape function within an element. So you remember that this is how we localize the elements, but this is how to think about how it really gets used in terms of giving this extra influence to the upstream portion. But these are the shape functions within a given element, which are this. And we just use those in the Galerkin method. So before, what did we have? We had A transpose dA. So this is our diffusion component. So instead of the derivatives of the normal shape functions, we now use the derivatives of these extra weighted shape functions, which are these. We could use, I suppose, we could use, if we wanted to, W transpose W. I don't think it would make any difference, right, from what we know about this product of shape functions. The product of these shape functions is just the total volume of the element. And I think you can probably show from what we just said about this area here being exactly offset by this subtracted area here, that if you multiply if you take the product of these shape functions, you still end up with the correct volume of the element, I think. I haven't tried it, but I think you would do. And so this is the capacitance matrix. So this is our storage matrix that we've talked about before. This is our diffusive or dispersive matrix, the second order term. This is our zeroth order term. This operates on dc dt, right? And the advective component here, this was our shape function before. B transposed V. So this is what our advective matrix looks like before. So we've just replaced the shape functions with the new shape functions. The derivatives of the shape functions with the derivatives of the new shape functions. And that's what we've used. And you can go through and calculate the matrix with that. So just by taking the derivatives. What else? There is a stability criterion. There's a term in here, obviously. So I didn't explain that perhaps in great detail, but these are just functions of location in the element, relative coordinate in the element, and relative coordinate squared. So this is a term. This describes the magnitude of the upweighting. Obviously, when this term is 0, then it's just a linear shape function. When this term is equal to some bigger number, then probably with a ceiling of 1, I'm thinking. Yeah, with a ceiling of 1. When this is equal to 1, then it's maximally upwind weighted. And so you can index this, the magnitude of this weighting parameter with the Peclet number. You have to be careful because you, obviously, if this is a very small, well, okay, is that right? So if Peclet number is very large, it'll be 1. If Peclet number is very small, it'll be negative, so you don't use a negative one. It can't be less than 0. So I guess you should be aware of that. And I think the actual expression for this is you can show that this is a hyperbolic cosine expression, but it asymptotes to this general behavior, and it allows you to calculate what the magnitude of this weighting of the shape function should be as a function of the velocity, where the Peclet number is the local Peclet number. Velocity in the element, length of the element, dispersion in the element. And just as an example of that is using this technique to be able to solve our simple one-dimensional flow problem in 2 different ways. One where you use, I guess this would be for an upwind weighting of 0, and you get this oscillation around the front, upstream condition of 1, downstream tacked at 0, a length of 2. This was the example we did before, and if you solve it using just the regular Galerkin method, you get this oscillating behavior around this mean value, obviously attached to these boundary condition values, which they both honor. But with upwind weighting for a relatively high level of weighting, you end up with a moderately good response, concentrations that make sense, concentrations that don't quite make sense, larger than 1, but a small amount of overshoot in this particular region, but otherwise it satisfies the conditions you'd expect. What you don't know, of course, is whether it's a true solution to your problem. It's constrained in this way, so I'm not sure how to determine one way or another, but the more problematic case, I guess, is this. And that is that as a result of using this, if the front should really be quite sharp, because it's advection-dominated flow, it might be that your solution comes out to give you a much more shallow front because it's adding what looks like dispersion. And so real dispersion in a system would make the front look not sharp, but relatively shallow. And so this idea of numerical dispersion may be something that's effective. Okay. Right. So that's all I wanted to cover with this today. So it doesn't mean that I'm going to stop talking, of course. It means that I'm going to go and open Hammer, I think is what I do. Maybe I can open, I guess I can open it here. And so what do I want to do? I want to do that. I want to do, I guess I can do Let's see if I can get logged in. Always says that, but I never quite believe it. So what is it I need to do? Can anyone remind me? Is it load? So I can never remember from one time to another. I will do this. Remind myself. Load COMSOL 35A and COMSOL. Okay. All right. Load COMSOL. Was it this? Or I think it's the other way around, right? Was it load? What am I doing?
Module load.
Sorry?
Module.
Module load.
The other way.
Other way, other slash. Looks like it. COMSOL. Thinking. So, what do we know? Okay, so I guess what we know is that we can deal with problems, multi-dimensional problems, using this advective component. The mechanism by which we do that is exactly the same as for transient problems for diffusion, except we have this extra advective term which gets added into the conductance matrix. Depending on our choice of time step and element size, we may have some issues with stability, which we can explore. And I guess also implicit in this, and will I lose this if I get off? Is that what it? Does it dump it if I move off this screen? I'm not sure. No, it doesn't.
It doesn't.
It made me sign back in. Oh, well, anyway,
I mean,
so,
that-
okay, all right. It's not on my machine yet. And the other thing is that if we want to be able to couple problems, you'll remember that if we're solving the flow problem, we have something that looks like, depending on how we write it, storage times the change in head with time is equal to hydraulic conductivity times second order of head, and we have a system that looks like change in concentration with time is equal to diffusion second order and concentration. And so clearly this velocity, this is really the first of our linkages, right? Because we need to be able to solve this, to be able to solve for Darcy's law. Divided by porosity, to be able to get, if this is advective velocity in this, we need to be able to figure out exactly how to get this magnitude of velocity. And so we need to solve one system equation as the input to the other. So let's mess around with COMSOL to see if we need to figure out, if we can figure out how to do that. And so the way to be able to do that is to, well, we could go, I guess we could go to the Earth Science module. Does it work? Does it not work? Is it frozen? Okay, so does it still exist anywhere? Doesn't look very promising that it likes to keep that little thing there, don't you think? Okay. Okay. Yeah. So let's do this. Just clear it out. Yeah, nothing else is open. So okay, let's try it again. This. Okay, blah 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 blah. I guess module load COMSOL. Okay, let's see what it does. Oh my god. Okay. No idea what that would mean. Module. So, what do you think we should do? I'm not sure what. Don't actually know what to do other than. Not sure that logging back in is necessary. Maybe starting up this again. It says login failed. Don't know if it's the speed of the connection or the lack of it, but this maybe looks.
Yeah, the connection in this room is terrible.
It's okay?
It's terrible.
Terrible. Yeah. Are you using up my bandwidth? So I do. I guess okay. So all right. So let's see if we got so. So let's. Yeah. Okay. Let's do these together. So I am going to do this. Okay, don't need that, and I guess since we did everything in the hydraulic head, so let's do these both at the same time. And so we can add those two components. Don't know how they're linked. I typically, so I want to do a couple of things. So let's pull together a geometry. Let's run it. Let's run it with some Peclet numbers and see what the behaviors are that we get out of it in terms of stability. And let's see if we can then link these two modules together, or see what the linkages are between these two modules inside COMSOL. So that's really all we're going to do. We're going to do it in 2D, so that should be fine. So let's figure it out. So let's do a one-dimensional problem in terms of size. So I'm going to make a geometry that is not really, no, I guess that's okay. I guess it's the same on both sides. So yeah. Okay, this puts in the middle, I think. It does. Maybe easier. I want. I'm just going to try and shrink it so it's one-dimensional, more one-dimensional, but it doesn't matter. We can make it one-dimensional by our boundary conditions. All right, so we have subdomain settings and boundary settings. That's what we need to define. And so we have two different behaviors. And so, okay, so let me just back up it. So I don't know how familiar you are with this. So we've chosen two different modules. And so it may well be that these are already linked and straightforwardly linked inside COMSOL, but we could also have taken modules that are intrinsically unlinked and provide those linkages ourselves, which is really what the kind of essence of this class is. I don't want to go back to the same slide, but you remember we have these matrices where we look at problems with flow and transport. The terms that involve nodal values of heads or concentrations and time derivatives of heads of concentrations and fluxes in this large 4x4 matrix. We've talked only about the terms that exist on the leading diagonal. The linkages between those different modules in terms of this is one of the terms that lives on the off-diagonal term. And so you can supply that to be able to take all of these individual modules that you'll have within COMSOL, and you can supply that yourself to be able to provide the appropriate linkages to be able to make it do the things that you want to do. And so these solutions exist here. So what we can do is we can put some boundary conditions in, maybe for the first one of these, for solute transport. We need to put in what the subdomain behavior is and its settings. So this is the differential equation here. So this is the velocity. This is concentration. The only other terms that we were, I guess this is steady concentration, is not transient. Don't see a transient term in there. Okay, well, let's go with it anyway. And so the values we need are for velocities in the x direction and in the y direction. So let's make our system so that it's, I presume x is this direction and y is this direction. So if we're doing something one-dimensional, then the velocity in y is 0 and the velocity in x is something. Okay? Apply. Okay. We want to apply boundary conditions. So this is our left-hand boundary, pardon me. So we have some choices of either prescribing a concentration or a flux, a mass flux across there. Let's apply a concentration that mimics what we've done before. So concentration of 1 upstream, 2 downstream, or not down, 2 downstream. See if we can make it 0 as we had before. The off terms are no flux, so there's no flux out of the side for top and bottom. So, and okay, what else do we need to define? Did we find a diffusion coefficient, dispersion coefficient? We have a value for, this is very, very complicated all of a sudden. So, it's more complicated than we need. So, let's see if we can make it more more straightforward. So these are velocities. So in terms of diffusion, dispersion coefficient, what's it doing? This is pore volume fraction. Okay, let's do this. Let's go back to this. Let's make life easy for us. Let's do this. So we can do this. We can provide so I'm going to do this, and I'm going to do this. All right? No. Okay. So you tell me exactly what I'm trying to do. Okay. All right. So there are 4 sets of equations in here, and they will all run if we give them appropriate boundary conditions. But I want to solve this problem of flow with some velocity in it, carrying some concentration through the system. So these 2 expressions. So what I could do is I could solve the flow problem. And the flow problem will be just this component, which if it was a diffusion equation, would just be the terms neglecting the advective term. And so this term here, for diffusion, I'm going to use to solve for the flow part. And this convective diffusion part, I'm going to use to solve for the other one. So I'm going to get rid of these. We could keep them there, but I'm just going to get rid of them because it makes it complicated. And so I'm going to remember the fact that this is concentration. Actually, the other thing you'll see, if for instance, we added another one of these for... You'll see that this marker here has this suffix 2, and these are the magnitudes of the concentrations that are the dependent variables in these equations. And so it indexes the dependent variables that it will solve. So if we wanted to, we could solve these 3 problems parallel to each other with boundary conditions that we apply that are different to each other, and they'd run completely independently and give us a solution. But we could also link them via this velocity term between this. So that's what we're going to attempt to do. So I can get rid of that. I don't need that. And so I'm going to go back in here. I think I have to go back, and I will. So the diffusion part is my flow equation. And so the subdomain is going to be, we're solving this. This is going to be hydraulic conductivity, and this is going to be head, right? And so hydraulic conductivity of 1. And initial conditions we won't put to 0. We need to know those. And I'm going to accept those, which is fine. And then I'm going to put some boundary conditions on it, which are going to be upstream on the left side. It's going to be a head of 1. I mean head because I'm using it in that. It's insulated on both sides, and the downstream head is 1 also, is 0 rather. Okay. So if I run that, so this is the geometry I have. So you know head is equal to 1, head is equal to 0. Velocity is equal to hydraulic conductivity, which is our d value, times the gradient of head. So you should be able to tell me exactly what the velocity is going to be. It's going to be equal to whatever this length is, which is 1. So this is 1, this is 1, so the velocity should be 1 as well. And so I'm not sure what this is showing. This is showing the... What is this showing? Okay, so it hasn't actually or is this at time 1? All right. And so the other thing I want to do, maybe I want to do it stationary. So let's try that again, see what it gives us. Oh, that's no good. So what am I not doing? So this is diffusion part, this is concentrations. What have I not done? 1, 0.
Because that's C2, that's concentration 2.
Ah, okay. So I'm plotting the wrong one, yeah? Or it's plotting the wrong one. And this is C2, and actually that system is C3. Okay, so all right, okay. So this, okay, so I need to, this is this, right? It's not cross section, is it? Global variables? Not that. So I want, is this the one? Was it plotting C2 or we set C3, didn't we? Is that right? Yeah, okay. All right. Thank you, Shane. That's great. So is that right? So it's upstream is 1. This is 0. So I guess the other thing I suppose we could plot we could plot what the velocities concentration gradient is going to be 1 as well, right? Should be uniform. It's about 1. And I suppose we could plot the velocity if we wanted to. So anyway, so at least it's giving us the right magnitude for this. Doesn't want to do it in the same window, but that's fine. So we have this represents, C2 represents the, so this is actually C2. And for the other part, time. So we'll do this, and we'll set boundary conditions. So subdomain, we want, this is C2. Was it C? Yeah, okay. Initial condition 0. This is our diffusion coefficient, which is uniform. Has no velocities in it yet. I suppose we could put a number in there in a minute. And so that's fine. Let's put in the second parts would be boundary conditions. Boundary conditions would be concentrations upstream, concentrations downstream, and if there's no velocity in the system, then we'd expect when we run it that the gradient in concentration should be from 1 at the upstream on the left to 0 downstream on the right. I suppose this is C2. This is the correct one to look at as well, right, for us? I think, right? And if we were to make a cross-section plot across it, then going from x equals minus 0.2 to x equals 0.8. Doesn't really matter where, so long as it's in the domain. I guess it might be better to have it in the middle. Oops, Control V doesn't work. Okay. Apply. So, okay. What doesn't it like? Oh, it doesn't like this. Yeah. So it gives the concentration to be upstream and downstream. So if we give it a velocity, so positive velocity in the x direction. So I guess it doesn't really need the plus. See if it likes the plus or not. So what's it? I guess the question is it going to solve this? So what have we done? So we've put a diffusion coefficient, I think, of about 1 in there. We put a velocity of about 1 in there. And so depending on the element size, it's going to control this. So our whole domain is equal to 1. So this is probably, I'm not sure, we can look at what the mesh looks like. I guess if we just do this, we'll know exactly what the mesh looks like in terms of size. So it looks like the mesh size is about, certainly less than a tenth. So this will be about, looks like there's 20 elements on one side to me. And so the Peclet number should be okay. So we should get a result that makes some sense, hopefully. See if we can run this. Is this on the right parameter? Yeah. And you see, instead of this two-part component where we had two elements in our system before, now it's completely curved. Of course, we can play games. So if we think that this is going to have to be, if the Peclet number is about a 20th here, I suppose we can get it to 1 by using a velocity of 20. It should work okay still. So we could try that. Well, actually, let's do this first, since we know this works. So instead of now it's flowing upstream to your left, and so it's depressed. And so we can go back in, and whoops, and do this, and we can do this. And now we can do, this should still be okay just, right? It certainly, well, it doesn't, it stops at 1, so it seems to be okay. So that's a Peclet number of 1. I guess we could be a bit more radical. We could increase it again. And so if we increase it to a Peclet number of 10, oops, oh yeah, I didn't rerun it. Solution. Yeah, so you see, not so well behaved anymore. Has this overshoot part, and so I suppose we could try and take care of that. So now we know what is it? We think it's a Peclet number. It is 200, right? So what is the size of this? So its velocity is 200, so 200 over 20, so it's about 10. So I suppose we could make it 1 if we have a tenth of the size of the element again, right? So we could probably do that appropriately. So rather than changing this, I suppose we could look at the elements, and instead of doing that, we could try and make them, don't know if that's a 20th. It's pretty fine though, right? So see if this brings it back. Solve it. Might take a bit longer, but not very long. Yeah, and so it actually kind of recovers it. And you'll see that with this extra, if we did it with a coarser set of elements, remember this distribution of concentration was further to the left. And so this one is being allowed to be closer to the right now, merely by virtue of fact. Now it's regained its stability, but also now it's discretized, and it's a better discretization. And I'm trying to think what I think the solution to the problem should be just, if you think about it physically, the physical interpretation, I think, of this system is that all of a sudden you have stuff being washed from upstream. It comes down at this concentration. So this is concentration here. And at this point here, you require all of a sudden the concentration to be 0. And so this component gets washed down here. The analog, I think, is of something being transported through a flare by some advective velocity, and you have some kind of cross flow in a very permeable layer, which is just shooting across here at some very, very large volumetric flow rate that takes the small portion of dissolved component that emanates from this this portion of the maybe a low permeability layer, and just washes it out and sets the concentration at that point to zero. And so the solution for that, just physically, should, I think, be something that would be basically this, almost a heavy side function, infinite gradient here at this point. So it's trying to be able to represent that. The one thing I didn't do yet is the other thing we can do is we could put in a value, and I'm not sure I know, it's been a little time since I've done this, is the way to link these is pretty straightforward. The way to link this would be to take this information that is present within this convection diffusion part, and we have a subdomain setting, and within this we have a value for a velocity here. What we could do is we could substitute that with something that represented the flow velocity in this other system. And let me see if I can remember how to do that. So what is our flow velocity going to be in this system? This is our equation. So we're saying that if this is an analog for our flow equation, then this would actually be, in this terminology, del dot d, which is diffusion coefficient, times the derivative of C3, which is the same as our k d2h dx squared, right? So this is our head, this is our hydraulic conductivity, and therefore the velocity is going to be equal to our hydraulic conductivity times the derivative of C3 in general terms, right? This is our hydraulic conductivity times the derivative with respect to location of the. And so let's see if I can figure out how to do that. Okay, not that. Yeah. I'm not going to be able to do it. So what we need to be able to do is to be able to substitute into this, into the box expression for the previous, an expression that does that. I'm trying to think exactly what it is. It will be something like open. It won't open with this one there, I guess. What's this underneath here? So it would be something like, it's not going to work, it's going to be some constant, 1 times I didn't touch anything. Yeah, something like that. So you see sorry. Yeah. So this is the derivative of C3 in the x direction, which gives the gradient of C3 multiplied by the diffusion coefficient. I guess there'd be a minus there, right? Just from Darcy's law. So this is representing Darcy's law. Hydraulic conductivity, a gradient of a term which we're taking to be the head in this particular case. Is that the right term? Actually, I wonder let's see if it takes it. No, it doesn't like it. Otherwise, it would make it. Oh, let's see. I can't imagine it'll run. Wrong apply. So let's see if it runs. No, it doesn't like it. So that's not quite the right term. But you get the idea. It allows you to be able to link the modules through these terms which are present on the off diagonal. And I guess I know we're over time, But just to go back to this, if you remember these relationships here, what we're doing, where would that fit in this particular case? We're driving concentration gradients in time, concentration gradients in space, and we're driving it by pore fluid pressures. So I guess it would be the term that goes here.